Hi, my name is Huan Doan. I'm currently an EBSRC Dr. Prize Fellow at the University of Bristol. It is my pleasure to give a talk today in the VANJ Conference 2020. And my talk today is about novel hierarchical porous materials for improved catalytic performance. Just a little bit about my research background. I have been working on synthesizing different types of porous materials, including zeolites, metal organic frameworks, and functional porous silicas, and testing these materials in various applications, such as catalysis, gas separation, and energy storage. The materials that I'm going to present today is a metal organic frameworks or a MOF, which is a new type of crystalline porous materials constructed from metal nodes and organic linkers. In most of the MOF materials, the metal centers can act as a Lewis acidic site, and the anionic ligands can act as a basic sites. This combination makes MOF being very promising in catalytic applications. In this study, we are interested in hierarchical plot structures where mesopores or macropores can be introduced into micropores MOFs. This idea can help, on one hand, to maintain high surface areas, on the other hand, to faster diffusion and mass transfer, and more importantly, to offer accessible surface areas, which is vital to enhance the reaction kinetics, especially when more and larger molecules can access to the active site in MOFs. In this study, we also tested the hierarchical MOF in some catalytic reaction to demonstrate the advantage of these structures and prove the concept that we have introduced. Here we took HECAS1 MOF as an example. In the conventional synthesis of HECAS1, copper ions and trimesic acid was mixed in dimethyl to make a stop solution. After that, a copious amount of methanones were added and left for at least 12 hours. Then the solution will filter and rapidly wash with methanol to remove the excess solvent in the pores before drying to obtain the solid MOF. In the CO2 method, we have demonstrated that we can trickle the nucleation and obtain HECAS1 MOF with similar yield by adding only 10 minutes methanol rather than 100 minutes as we need in the conventional method. This finding can help to reduce the amount of toxic solvents, which is great for green synthesis that we want to establish in the future of chemistry. Unlike other synthetic methods, using CO2 can minimize the risk of pore collapse during the washing step, which have been reported as a big issue in some MOF synthesis. We also carry out the view cell experiment and observe that a precipitate was formed within 2 minutes after introducing CO2 to the reactor, and a fully opaque mixture was obtained after 4 minutes, which is much faster than 12 hours using excess methanol. And this finding demonstrates that supercritical CO2 can introduce a rapid nucleations, which can help to reduce the cost of the MOF synthesis, even the high pressure is required. Our results show that MOF properties can be adjusted by changing CO2 pressure and reaction time, and the number of macropores increase with a longer exposure to CO2, and a finely divided network with interconnectivities was observed in the sample synthesized in CO2 over 24 hours. We demonstrate that there is a direct relationship between pressure and average particle size with the preserved framework of the pristine MOF. This finding introduced another factor that we can change during the MOF crystallization to finely tune the property of the porous materials. The possibility of adding larger pores and channels offer exciting prospects for the deployment of MOF as a catalyst. To prove the benefit of introducing macropores in catalysis, We took the sample synthesized in CO2 at 75 bar and 72 hours to compare with the normal head gas with only microstructures. First, we tested samples in a gas phase reaction, and here we use CO oxidation as an example. We can see that the head gas CO2 had a higher activity than normal head gas, which demonstrates that the CO molecule could access to the copper sites in head gas CO2 better than in normal head gas. So we can confirm that the existence of macropores indeed had to overcome diffusional limitations and increase catalytic activities of head gas CO2 in these reactions. We also compare the performance of hierarchical head gas 1 in a liquid phase reaction, and here we use the methanolysis of styrene oxides as an example. We can see that the head gas CO2 has enhanced catalytic activity than the normal head gas. And considering the similarities in the structures and the surface areas, we can confirm that the improved catalytic performance is due to more accessible macropore structure in these materials. We can also see a greater improvement in the liquid phase reactions compared to the gas phase reactions. This results evidence that macropores are beneficial in overcoming the diffusional limitations, which have a greater effect on reactions where bunking molecules are involved. To conclude, we have demonstrated that supercritical CO2 have some advantage in MOF synthesis. For example, an increase in the MOF formation and a decrease in the amount of solvent. This synthetic method can provide another factor to control particle size and porosities and provide an excellent route to synthesize MOF with hierarchical structures. Introducing this structure into MOFs have benefits in improving accessible internal surface areas and improving catalytic performance in porous materials. We can predict that the macropore structures will have a greater effect in case where the diffusional barriers are greater. To complete this talk, I would like to thank all the members in my group. And of course, I can't forget all the sponsors who have financial support me in this project. Lastly, thank you all for your attention, and I'm happy to answer any questions.